All right, I will begin, I think. It's time. Oh yeah, it's time. Let me start. Dear Father, we thank you for this day. I thank you again for this class. This opportunity we have just to meet together and study your creation. Just pray you guide our steps today. Help us to glorify you what we do, and just that the students would learn what they need to learn before the test this week, Lord. In your name I pray, Lord Jesus. Amen. All right. Probably we should do some more examples. Let's see here. How about this one? Example 1. Suppose you've got like a half cylinder like this. All right. And let's see here. Let me say that's what are we talking about here? This would be something. What would be the equation of a half cylinder like that? Can you guys tell me? So if you look at this, every stage of the game is the same for x, right? It's the same curve in the x direction over and over and over again. That means x cannot be involved in the formula for that, right? So it has to be something like y squared plus z squared, let's say, equals to, let's make it 4, just for fun. And apparently z is greater than or equal to 0, right? Suppose then I want to, for that shape, but suppose that I do something annoying, like I cut it with a plane that goes like that, and make that the base of it. So instead of above z equal to 0, I give this as the new bottom for the volume. And I want to make that a plane. I want it to be a plane that goes through this point and that point. Let's see here. So I guess I need to tell you how far the cylinder goes out, right? How far do you guys want it to go out? This is x equals to what? To 12? Okay. It's kind of random. I'll allow it. So in that case, I think what I need is x is equal to 12 plus, well, goodness gracious. This point up here is what? 0, 0, 2. So like the plane I'm looking for here is something like I want it to go through x equals to 12 when z equals to 0, right? And I want it to go through 2, so I guess I want minus some number times z. 5z, is it? Would that work? When z is equal to 2, I get x is equal to, oh, that's not what I want. I want x equal to 0 when z equals to 2, right? So maybe that'll do it. X equals to 12 minus 6z. So if I put z equals to 0, I get x equals to 12. If I put z equals to 2, I get x equal to 0. That's what I want. These are these 2 points that I'm specifying. And then and basically this plane is kind of boring. It's just the same in every y. All right. So you can imagine then this shape here, right? I will foolishly attempt to sort of illustrate it. Here it is. It's, you know, something like that. And then solid in here as well, right? So it's like a, I don't know, I'd say a loaf of bread kind of sliced weirdly, if you had that kind of, but nobody has a loaf of bread that looks like that either. I don't know. So, all right. So then how do we find the volume of such a thing? So the description of it is this. We have, so I think it's most convenient to think about this in terms of z. This is what? This is x plus 6z equals to 12, also known as z is equal to 12 minus x over 6, aka 2 minus 1/6 x, right? So we have, and what's the equation for the top of this volume? Well, I think the equation for the curved part up here would be z is equal to the square root of 4 minus y squared, right? Now that does depend on y, as it ought to, right? Like z is largest when y is equal to 0. That gives you sort of the top of the cylinder, the half cylinder. And we don't have the minus because we're up here, right? Okay, so getting to the point. We have 2 minus 1/6 x less than or equal to z less than or equal to the square root of 4 minus y squared, right? That is the sort of complicated, most complicated aspect of this volume. But what I would start with probably would be, well, what, you know, I mean, I would start with x. I mean, I would make x the outside bound, but that's kind of the most lazy of all the inequalities to describe the volume, right? I would start with that one, which is what? X is going between 0, all the way out to 12, thanks to Sam, right? So 0 less than or equal to x less than or equal to 12. Basically, I start with that. That's what I start with in my thinking. I do that first. And then I want to then the second thing I'm going to do is I'm going to cut out the half cylinder. How do you cut out the half cylinder?
You mean like plus or minus root 4 minus z squared?
Yeah. I think that's what I want to do. Sorry, just a second here. Let me think. What did you just, let me write down what you just said. What did you say?
So from negative root 4 minus z squared to positive.
So that's the y, okay. Let me see if I believe that.
You also need the intersection. So at the base of the cylinder, why does it go all the way out to the sides?
Yeah, let me think about this for a second. So that's your y. Y is going between. I don't think that, I'm not sold on this just yet. What are you saying, Sam?
At the base of the cylinder, why won't have any width then just at that one point? Probably go on the wire. So you'll need to find where it intersects with that plane as in the domain of the line.
Um,
Changing the parameter station or
I don't think we're right yet. I mean, I should be able to think about it in terms of cutting three-dimensional shape down, space down. So if let me just go through the stages and see if I can understand. This comes first, right? So to start with, we're just, we've got this slab that does what? It goes on and on both ways, this way and that way, right? But this is x equals to 12, and this back here is x equals to 0, right? So that's step number 1. Step number 2 would have to be the one that's right under it, right? What would that look like in terms of the cutting? What is that doing? This upper one is from y squared plus z squared equals to 4, right?
We go y squared plus y squared.
What's that? Oh, good grief, thank you. My bad. There we go. Sadly, that is not a good sign. So that circle, right, is okay. So that then, if we do that, what's that do? That cuts out. Sorry, I have a hard time thinking sometimes with these. Why? Well,
you did constrain C between that plane and the top of the center.
well, I'm ignoring that. We geometrically, I have to think the least to the most complicated. That's the last cut, not the middle cut. So in terms of like sculpting shape down, I start with the outer bound and work my way in. That's the finishing touch. That's the last cut, I believe. What I'm trying to think about is, what does this mean if I add this to that? Okay? That's what I'm having trouble seeing at the moment. I mean, that's a circle, right? In the YZ plane. Is that just cutting, is that just drilling out? Is that just drilling out a cylinder from this? I think it is. Because that gives you y squared plus z squared equals to 4 at every x, right? So this fixes y to be between, well, let me do some color coding here. So that would fix y to be between like the front side, like here, right? That's given by this one. And the back side, like that, right? And then once you have that cylinder, right, which you could imagine, by continuing this thing here, right? And then we cut off, well, then you just cut like that, right?
The issue is you have y and z in terms of each other.
Ah. Yeah. Let's think about this schematically. So we have committed to 0 to 12 for my outside bound, right? We're struggling with what to put here and here. We've more or less decided that we're going to put 2 minus 1/6 x here, and the square root of 4 minus y squared here. And so we're doing the dz, then the dy, and then the dx. So what do I need to put here? Yeah, I'm only allowed to have, only allowed for functions of x, right? Okay. So while what Shane told me is relevant to the problem for sure, right? I mean, that does describe everything going on in here fits inside that. True. But it's not the one we're looking for in terms of the current description. So what should I put there?
Could you maybe solve for z and substitute it?
Solve for.
Like with x equals 12 minus 6z. Then you put it on the other one, you get the relationship between x and y.
So find the intersection between the cylinder.
I think we just want. Oh, my bad. So we need to think about the shadow of this space into the xy plane is what we have to do. All right, because that's how you think about this. So I have to think about what's the shadow of the volume into the xy plane. That's how I cipher what goes here. So what is the shadow of this volume into the xy plane? If I draw it like this, maybe we can sort of see it. So here's my y, here's my x, right? So at 12, it's like this. And what you just said a second ago might be what I'm about to do, but I didn't quite track with you because I'm thinking. And so it's something like this, right? It goes to a point as it cuts up to that singular point up there, right? So the question is, what is this shadow? Okay, so what are these curves here is really the question, right? They're elliptical, okay. But how do I get the equation of them? I mean, so we have 0, we've got 12. The question is about these guys. That's what we're interested in. How do we get those? Those are from what? The intersection of what and what? Intersection of plane and cylinder. So how do we describe intersection of the plane and cylinder? So the plane is defined by this one, right? And the cylinder is defined by this one. So it's where both of those equations are true. I think one of you told me to solve for z and stick it into the other one a second ago, and that's exactly what we want to do. So solve this for z. Oh, I already did. So we get y squared plus 2 minus 1/6 x squared, right? Equals to 4. And so the hideous, horrible thing we want to put here is the square root of 4 minus parentheses 2 minus 1/6 x squared. That gives me this one, right? And solving this, the other one is the minus root. So we get minus the square root of 4 minus parentheses 2 minus 1/6 x squared. Yeah. And there you go. That would be the volume of this monstrosity. Now, if I was actually going to try to calculate this, I don't think I would calculate it the way we're currently doing. I mean, I would set it up in the way we're doing, but I probably would introduce coordinates. What coordinates do you think you'd use here?
Cylindrical coordinates with r, theta, x.
Right, yeah, I think I would use cylindrical coordinates. I would use modified cylindrical coordinates. I'd use cylindrical, quote unquote, and the cylindrical coordinates I would use, they would be, x equals to x, y is equal to s cos beta, and z is equal to s sine beta, something like that. See, because x is playing the role of z, and we're talking about a cylinder that has z as x as its axis. So if I made that change of coordinates, then I should be able to do this integral with a little bit less pain. But I'd still have to think a while about it. And I think we should probably go on, but this has hopefully served its purpose. So I have a really hard time teaching this material because you guys will, in the middle of me setting something up, say something that's eminently reasonable, just irrelevant, right? Like this. Totally reasonable. Like this is on point, but it's not the description we have to have given the order of the integration, right? So again, just to recap, the idea is if you're working in Cartesian variables and you're thinking about your outside integral, that sort of picks a giant slab to work in, but to figure out what to do with the other two variables, you have to think about the projection of the volume onto the remaining coordinate plane and work from there as if it's a type 1 or type 2 setup. This all supposes that the volume looks like this. Like not all volumes allow this kind of decomposition anyway. There are more hideous things which require you to break into like two pieces and do the two pieces separately. Violet says, ew. Yes. But anyway, let's focus on the part you guys are actually stuck on. Example 2. Let's work on something easier here for a second. Suppose I'll work this example again because I think it could bear repeating. We're looking at, let's see here, this time I'm just going to give you these points. 0, 4, 0, 0, 2, 0, and we'll put this one out at 6, 6, 0, 0, right? I can say calculate the integral of xyz dv over E, where I'm saying E is xyz such that xyz is greater than or equal to 0 and below plane P. There. How do we do this? How do we set up this integral? So let's follow my instructions that I just laid out. Number 1, pick what you're going to, well, let's see here. I mean, there's two ways to go, right? The two ways to go are the one way is to pick your ugliest bound, start with, right? And then think about the projection with respect to the ugly bound, which comes last. The other way is to make your, so you guys, what do you guys want to do? Do you want to start with the inside bound? Do you want to start with the outside bound? We can go either way. Yep. Oh yes, thank you. Yeah, first we probably better make this not insane, so that would be good. Thank you. So then what? I'll start us out. I want to think about 0 less than or equal to z less than or equal to what's the equation of this top one? How do you figure out the equation of a plane with 3 points? Cross product of 2 points. I like the spirit of what you're saying, but the mechanics, not quite right. So I need 2 vectors that are tangent to the plane, right? So how about this? If I have this vector, and if I have that vector, then totally on board with you would take the cross product of those two guys And that'll give us a normal to the plane. Absolutely. Totally agree. So what is that actually? We got what? Minus 6, 0, 2. Cross product with minus 6, 4, 0, I believe. And so that gives us, I'll use the determinant mnemonic, if that's okay with you guys. What's that give us? X hat, I get a minus 8. Y hat, I get a minus, 3 minuses, so minus 12, I think. And Z hat, I get a minus 24. Let's check on that. Does the dot product of this vector with those two equal 0? I get 8 times 6 is 48. 48 minus 48, 0. Woohoo! And 6 times 8, 48 minus 48, 0. Huh, so it's both 48 minus 48. That's kind of funny. Anyway, so there's your normal, but you don't use that. Let's see, factor out like a 4, maybe a minus 4 even. And minus 4 would give me what? 2, 3, 6. Yeah. I'm going to use 2, 3, 6 as the normal because it's less weird. So, and what's my equation? Well, pick any base point you like. I'll use the 6, 0, 0. So 2 times x minus 6 plus 3y plus 6z equal to 0. There's the equation of the plane. Solve for z. And we've got what? We've got minus 1/6 times 2 times x minus 6 plus 3y. Now you could arrange the minuses differently if you want, but I think that's it, right? Yeah.
Why doesn't z just go from 0 to 2?
Oh, because we're setting it up this way. And so because we're setting it up this way, we have to think about the projection of P into the xy plane. So, you know, here's my, I'll draw the picture like this again. Maybe it's helpful, maybe it's not. I don't know. This right here gives me this line here, right? That point is at 6. This one is at 4, right? And so that gives me, and of course this is all the z equals to 0 projection. So z equal to 0 into this here gives me, of course, you know, let's see here. So this being 0, I get 2 times x minus 6 plus 3y equal to 0, which of course we could solve for y is equal to minus 2/3 x minus 6. You can check us, let's check ourselves on that. If I put x equal to 6 into that formula, I get y equal to 0, yay. If I put y equals to 4 into this formula, then I get 12 divided by minus 2 is minus 6 equals to x minus 6, x equal to 0. Hooray, it works. So it goes through both of the points that I want. And now, all right, so now that I see that, I have 0 less than or equal to y less than or equal to minus 2/3 x minus 6. And that's for x ranging from what to what? X ranging from 0, right? All the way over to 6. So in total, we have then the integral we're up against, x, y, z dv, would be the integral from x equals 0 to 6, y equals 0 to minus 2/3 x minus 6, integral from 0 to 1 minus 1/2 of twice x minus 6 plus 3y. And then you got your handy dandy x, y, z, dz, dy, dx. Now, Violet said a minute ago, but doesn't z just go from 0 to 2? Or 0 to 2 you said? Right. Now I agree. We could look at it that way. Let's do that. Let's set up the integral in that regard. So you're saying you want to set up the integral. When you commit to z going from 0 to 2, you're committing to z being the last integral. All right? All right? And if you're committing to z being the last integral, right? That means either x or y is the first integral. Right? Now you choose. Which one do you want to be the first, x or y? Dx it is. See, once I choose that, that means in order to understand what goes on here, I need to look at projection of E into the YZ plane. Right? And I say projection of E, but really the projection of E here boils down to the the projection of the plane P. Right? So like what does that look like here? Can I erase the cross product? I don't think we need that anymore. All right, so let's see here. We've got to think about the projection into the YZ plane. X, Y, Z. So we're talking about this back here, right? Actually, this guy. So I'll put it up here. Here's Y, here's Z, at this point. Now, we know that this is 4. We know that this is 2. What's the equation of this right here? This is x equals to 0 and the equation for the plane, which I happen to have here. So you put these together, what you get? You get 3y plus 6z equals to 12. Now, you chose y to be this one, right? So y is the one that we need to look at here. I need to look at this. Okay, so y is equal to 12 minus 6z over 3. In other words, y is equal to 4 minus 2z. And if you look at that, let's see here. If we look at it this way, any point in there, we have 0 less than or equal to y less than or equal to 4 minus 2z. And then, of course, that's true for what you wanted me to do, 0 less than or equal to z less than or equal to 2. Right? So, all right, there we go. So I have my 0 and my 4 minus 2z here. And the inside bound, most exciting one, is, oh, we already had it up. Nope, excuse me, my bad. I need to do what? Explain how x is bounded. How does that go? How do I figure out that? What's...
Solve the equation.
Yep, solve the plane equation for x, exactly. So this gives me, yowzers, 2x is equal to 12 minus 3y minus 6z. So I have, and of course it's bounded below by the coordinate plane, so I have 0 to 6 minus 3 halves y. 6 divided by 2 is 3 minus 3z. There you go. So if we committed to 0 to 2 for z, then that's what I have to figure out for x and y. Yeah. Mm-hmm.
The one above it, that's supposed to be a -1/6, right? Not a -1.
Oh, let's see here. If you're asking me, probably, yeah. Yeah, oh yes, 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 thank you. Yeah, I failed to transcribe that from here, right? Whee! That should have gone to a 6, thank you. So I think what I'm describing is more or less an algorithm, right? Like, you pick, if you determine what your outside bound is, you just have to look at what's the shadow of your solid onto the projection of the other two coordinates. And then once you have that, it's a two-dimensional problem. You fall back into the problem of describing it either as type 1 or type 2, so to speak. Yeah, two choices. This, of course, all assumes that it's a quote-unquote simple solid, which allows for this kind of description. In other words, it's a solid which you could obtain from sculpting all of three-dimensional space by making a cut, and then another cut, and then a third finishing cut, right? But there are things that require more delicate sculpting than that. Like pretty much any sculpture ever made can't be described in this way. So to describe the integral over an actually interesting sculpture, you'd have to break it up into simple sculptures and then add the integrals up over those. That's where the U comes from, right? Very U. Any questions? Surely you guys have questions. Well, let's see here. You guys are gonna work me to death. So you guys are all done with your homework? When's the homework due? Oh. So you're not done with your homework. You don't have questions about your homework, but the homework's due tomorrow. This is not a recipe for success.
We go over 86.
86. If my computer will turn on. Huh? All right. Come on, computer. I'll find it eventually, guys. Let's see here. Which test are we on? I mean, which home? We're mission what?
6.
Mission 6. Thank you. I will eventually get to it. Ah, woohoo! Problem. Oh, hey, this is a second page question. That's good. That's good. Yeah.
Plug it in for that variable.
So you're given the density, which is the mass per unit volume, right, is equal to alpha rho to the power c where alpha and c are constants. All right. And blah, 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 blah. You're supposed to calculate the moment of inertia. So what do you guys think? How should we calculate the moment of inertia here? And here B is the solid sphere. I think I called it B sub r the other day. So like B sub r is equal to, you know, I'll just describe it this way. Rho less than or equal to r, right? The spherical angles are free. All right, so what, Michael, you have a question? Like, just generally how to go about it, or? Okay. So what so first of all, the problem just yells at me spherical coordinates, because setting up spheres in cylindrical coordinates does not give me joy. But you could do that. You could set up a sphere in cylindrical coordinates. It's probably a good mental exercise to do that. But let's focus on this here. So I would set up the bounds 0 to 2 pi, 0 to pi, 0 to r. That's my spherical. Now, r in terms of sphericals we talked about the other day, right? It is rho sine phi. And my delta, well, delta is an interesting thing here. It's alpha times rho to the power c. A lot of times we've worked with delta just a constant, but not here, right? And my dv, well, we worked that out. That's rho squared sine phi. And then you got yourself, and now I got to be careful to mirror the ordering of my bounds, right? So I've got d rho, d phi, d theta, and yeah.
What about your r squared?
Oh man, I missed the square, but that we can fix. I'll make my correction in red. Very good question, though. There we go. And then, of course, you can simplify this and integrate with respect to rho, with respect to theta, and with respect to phi. Now, I can tell you what's going to happen. Something interesting happens with a lot of these examples is you're going to end up with the integral from 0 to 2 pi, integral from 0 to pi of, like, you know, sine phi, d phi, d theta. And some people would call this is the integral over the solid angle d omega, which is 4 pi. So like anytime you have an integration, oh rats, I can't even say that here. Why can't I say that?
Yeah, the sine cubed.
I've got a sine cubed. It's spoiling my fun. So if example 3, what if instead I was doing the integral over br of, say, e to the minus rho squared dv? Well, then this would be, you know, the integral over d omega, actually, times the integral of rho e to the minus rho squared d rho. So you get like 4 pi minus 1/2 e to the minus rho squared, value of 0 to r. So we get like, you know, 2 pi e to the 2 pi 1 minus e to the minus r squared, if I haven't made a stupid mistake. But like, sorry, I wanted to talk about solid angle, but admittedly this homework problem is not the place to do it. My bad. This is called solid angle. So if you study spherical, it's like spherical trigonometry, which no one does anymore, but if you were, you know, a mariner from 200 years ago and you wanted to understand how to, you know, sail across the seas with charts and junk, then you'd probably want to know about spherical geometry and solid angles and things. But anyway, just a side comment. Other questions? No? All right, well, I'll let you guys go.
Math battle.
Math battle? Today?
Tomorrow. It's due tomorrow.
Oh, it's due tomorrow?
That's what it says.
I think the math battle is... Oh, man. I thought that was something I had to do tomorrow, guys. I'm sorry. Just a second. Let me think about this.
We could do it as a class. No expedite.
Well, anyway, class is done today. I don't have the math battle for you. You need to finish your homework anyway, apparently. So I will pick teams and assign math battles tomorrow, and then you'll have till Wednesday to do it. Because we still have Wednesday to talk about math battle before the test anyway, right? So that should be fine.